Hello everyone. Let's begin with a fascinating journey into how chemists prepare aldehydes and ketones, two of the most important functional groups in organic chemistry. Think of them as the backbone of perfumes, plastics, and even medicines. Now, there isn't just one way to make them. We have multiple methods, each with its own conditions and selectivity. Some routes start from alcohols, others from hydrocarbons, and some even from acyl derivatives. By the end, you'll see how these transformations are not random but tailored to get exactly the carbonyl compound we need. Let's start with alcohol oxidation, probably the most familiar method. When you take a primary alcohol like ethanol, represented as CH3CH2O, and gently oxidize it with acidified potassium dichromate or potassium permanganate, it gives acetaldehyde CH3CHO along with water. But if you oxidize a secondary alcohol like isopropanol, the reaction gives a ketone, acetone, with the formula CH3COCH3. The reagent decides the strength and speed, but the golden rule is primary alcohol goes to aldehyde, secondary alcohol goes to ketone. That's why industrial ethanol oxidation is a major source of acetaldehyde. Next comes dehydrogenation, a more industrial route. Imagine passing alcohol vapors over hot copper or silver catalyst at around 573 Kelvin. Ethanol, CH3CH2O, loses hydrogen atoms and becomes acetaldehyde, CH3CHO, releasing hydrogen gas as a byproduct. Similarly, secondary alcohols like isopropanol lose hydrogen to give acetone. The beauty of this process is its efficiency for volatile alcohols, making it perfect for large-scale chemical industries where aldehydes and ketones are bulk raw materials. Now let's turn to hydrocarbons. One classic method is ozonolysis of alkenes. Picture an alkene like ethene, CH2 double bond CH2, reacting with ozone. The ozonide intermediate is then broken down with zinc and water. What do we get? Two molecules of formaldehyde, CH2O. If the alkene is propene, CH3CH double bond CH2, the products are acetaldehyde and formaldehyde. So the location of the double bond tells us what carbonyl compounds will form. This is like surgical cleavage of the carbon-carbon double bond, giving us neat aldehyde or ketone fragments. Alkynes, too, can serve as carbonyl precursors. In this method, we hydrate an alkyne in the presence of sulfuric acid and mercuric sulfate as catalysts. For example, ethine, CH triple bond CH, reacts with water and rearranges to give acetaldehyde, CH3CHO. On the other hand, a terminal alkyne like propyne, CH3C triple bond CH, undergoes hydration to form acetone, CH3COCH3. Here Markovnikov's rule applies, which means the O attaches to the more substituted carbon, ensuring predictability of the product. Finally, a very elegant method, the Rosenmund reduction. In this reaction, an acyl chloride such as acetyl chloride, CH3CoCl, is reduced with hydrogen gas in the presence of palladium on barium sulfate. The poison catalyst ensures the reaction stops at the aldehyde stage, giving CH3CHO and hydrogen chloride gas. Without this precaution, we would get an alcohol instead. This method is especially useful for producing aromatic aldehydes like benzaldehyde, which have wide applications in flavoring and fragrance industries. So to sum up, aldehydes and ketones can be prepared by oxidation, dehydrogenation, ozonolysis, hydration, or reduction, each method chosen depending on the raw material and the desired product. These reactions are not just textbook content, they drive industries from pharmaceuticals to plastics. I hope you now see how these functional groups are produced with such precision. That's it for this session. See you in the next class, where we'll explore even deeper into the chemistry of carbonyl compounds.